couple of you have been raising interest about where does this come from or how to do this integral. So let me show you the trick. This is a slightly non-trivial integral. You can do it from elementary techniques through finding the right trigonometry substitution or playing around with this, sort of massaging this into an integrable form. But there's a neat trick to this if you know it. Yeah, so there's a couple of ways to do it, but I'll show you sort of a clever substitution that can transform this into a very easily integrable form. Okay, so don't feel bad if you cannot come up with this substitution on your own. This is just one of those things. If you know it, you know it. If you don't know it, you don't know it. Anyway, so let's get started. We can either look at this as a secant x or 1 over cosine x. But first, we need to know two facts on, that you need to know the integral, or you need to know the derivative, I should say. The derivative of tangent x is secant square x, and the derivative of secant x is secant x times tangent x. Okay, so these two facts we will be using. So before we go forward, let's just make sure we understand why. So let's call these results 1 and 2. For 1, you see that the derivative of tangent is really just sine over cosine, because that's the definition of tangent. You can either use product rule or quotient rule. Let's treat this as a quotient. So we have, we'll copy cosine up here, and then we'll differentiate sine, which gives us cosine, minus, we'll differentiate the cosine this time, and which is minus sine, and copy just the previous numerator, which is sine, and everything is over cosine square x, right? You square the denominator. So on top, we have essentially cosine square x plus sine square x, which we recognize from the identity. This is the fundamental identity, is 1, right? So it's 1 over cosine squared x, which is essentially, if we're lazy, we'll use the word secant to represent 1 over cosine x. Okay, so that's number 1. Number 2, we will have the secant x derivative, and this is very similar. We will switch this up. We'll write this as cosine x to the power of -1, so we can use chain rule. This is, be careful, this is not the same as cosine inverse x, right? This is notation-wise, the inverse means arc cosine. So personally, I always tend to write arc cosine x instead of something confusing like this. But yeah, so we'll stick with this for now. So we can use chain rule. So we will pull down the -1, this becomes -2, and then we will differentiate whatever's inside as a chain. All right, so now we will rewrite this. 2 minus signs cancel out. We'll rewrite this as something neat. Yeah, so that's the result. Okay, so this can clearly be written as this as well, which is secant x times tangent x. Okay, so we understand these two results here. Now we will be multiplying to solve this integral. We'll do a smart smart sort of trick. Again, it's one of, like I said, it's one of those, if you know it, you know it. If you don't, you don't. All right, so I'm going to multiply by 1, essentially. I can multiply by anything by 1, or a fraction where the top and the bottom is the same. So I'm going to multiply by secant x plus tangent x on top and bottom. All right, so essentially I'm just multiplying by 1. Okay, just to be clear, that's a multiplication. I can always multiply something by 1. It's not going to change anything. Okay, so I'm multiplying that. And then now let's simplify on top. I have secant square x plus secant x tangent x. And on the bottom, obviously, it's just what we have there. Now we start to recognize some of these factors, right? You see the top over here, basically, I noticed tangent x, I noticed secant square x is essentially the derivative of tangent x. So let's rewrite this a little bit. I'm going to put the dx to the right-hand side. So I'm going to write d tangent x is equals to secant square x dx. I'm going to move this dx to this side as well. right? So essentially on here, we have secant square x dx plus, I'm just going to multiply the dx on top. You may or may not have be comfortable with seeing this before, but yeah, this is also fine. It'll make things easier to recognize. Okay, so now we look at here, you'll see secant square x dx matches this completely. I can replace it with d tangent x plus, and similarly here, it's secant times tangent times dx. Notice secant times tangent times dx is literally d of the differential or implicit differential of secant x. And we, because derivatives are linear, we can write d tangent x plus secant x like this. Okay, we can group these two together because they are basically linear. Derivative basically just hits on linear, meaning you can distribute this. It's distributive essentially. You can distribute this into each term. Now you see the top and bottom are of the same factor, right? So essentially I have something that looks like, and have something that looks like 1 over something be something, right? So we recognize if, for example, if I write it like this, we will all recognize this as log x plus c. I'm gonna skip the plus c due to space at the moment. But essentially the idea is x is just a dummy variable. This could be integrate 1 over happy face with respect to happy face. Then I'm going to have a log of happy face with the face there. So now I have here 1 over this chunk with respect to this chunk, right? It's the same situation over here. So it's just log of this chunk. Remember the plus c, right? So basically the answer is log of secant x plus tangent x plus c. Okay, so that's the result, right? So I'll just quote this up here, either 1 over cosine x, you can write it like this, or write it as secant x dx. Either way, the answer is log of, remember there's always an absolute value in the log plus c.